One of the most puzzling paradoxes in navigation is that the speed of ships and aircraft is measured in a unit that has nothing to do with the mile, the unit most modern maps rely on. We tend to think of speed as simple distance divided by time. Yet maritime navigation chose a measurement that does not match any land-based standard. That choice was not eccentric. It was driven by the shape of the Earth and the need to describe motion across a curved surface using the simplest possible tools. If we trace the rope tied to that floating wooden block centuries ago, we discover not improvisation, but a geographic calculation precise enough to make early computers seem cautious by comparison. The mile developed in a completely different context. It described distance across flat terrain, suitable for Roman soldiers marching in step, where distance was counted by paces. As civilization expanded toward the open ocean, this unit became disconnected from the surface it attempted to measure. On a flat map, you can draw a straight line with a ruler. On a spherical Earth, traveling straight means following a curved arc along the globe itself. The mile has no built-in relationship to spherical geometry. It was never designed for that purpose. Sailors understood this reality clearly as they stood on deck. The distances they traveled could not simply be translated into land-based measurements. Latitude and longitude formed the true map of the ocean. 1 minute of latitude corresponds to a fixed distance on Earth's surface, observed across long voyages. This distance proved far more consistent than any unit derived from footsteps or wagon wheels. At that moment, the mile lost practical value at sea. A new unit had to be defined not by habit, but by the geometry of the planet. The remaining question was how to measure it with the simplest equipment imaginable. The familiar image of a wooden block tied to a rope hides a carefully calculated system. The rope was not marked at random intervals. The distance between knots was set at 47 feet, 3 inches, a number that might appear arbitrary. In reality, this spacing was the key to converting a ship's motion into movement across Earth's surface. The mechanism was elegantly straightforward. The wooden block was thrown overboard and resisted the current, creating a nearly stationary reference point. As the ship advanced, the rope slipped through the sailor's hands. A 2/8-second sandglass was flipped. During those 28 seconds, the number of knots passing through the sailor's fingers represented the vessel's speed in knots. For this to work, each knot had to equal precisely the distance the ship would travel in 1 hour at that same speed. By combining the length of rope released in 28 seconds with the conversion to a full hour, sailors effectively measured nautical miles per hour. And a nautical mile is defined as the distance corresponding to 1 minute of latitude on Earth. That specific length, 47 feet 3 inches, when multiplied appropriately, aligns almost perfectly with 1 nautical mile per hour. This was not guesswork. It was deliberate mathematical encoding, built directly into the rope itself. The elegance of this system explains its endurance. When steamships replaced sailing vessels, mechanical propellers and underwater rotors replaced wooden logs. Yet the knot remained unchanged. Sailors were accustomed to the idea that 1 knot equals 1 nautical mile per hour. And a nautical mile is anchored to Earth's geographic grid. A system so deeply integrated into planetary geometry is difficult to replace merely because materials or engines evolve. When aviation emerged, navigation demands grew even stricter. Aircraft move in 3 dimensions, but their routes are still projected onto latitude and longitude maps. The nautical mile remained the most compatible unit for describing that motion. The mile could not serve this role, because it lacks any geometric connection to Earth's coordinate grid. The kilometer fits neatly within the metric system, yet it does not align naturally with the maritime navigation framework that early aviation adopted. So when a pilot reads 450 kT on a cockpit display, that number represents a modern continuation of the same logic once measured with rope and sand. Pitot tubes, onboard computers, and navigation software have replaced wooden blocks and hemp lines. But they have not replaced the fundamental unit. The underlying principle that speed must correspond to the planet's geometric structure remains intact. 1 knot does not equal 1 mile because a mile does not describe motion across a curved earth. The rope marked at 47 feet 3 inches between knots was calibrated to reflect precise movement relative to latitude. When aviation inherited the task of high-speed global travel, it retained the knot because it integrates seamlessly with the global positioning framework. This story reveals why many measurement systems persist not out of tradition, but because of deep structural compatibility. If you find it fascinating that simple tools can contain entire mathematical systems within them, there is always more to uncover. Many ancient instruments still hide quietly inside the modern technologies we use every day.